Tonight's speaker is quite esteemed. He's designed systems to support science missions for NASA. No kidding, guys. Please welcome the senior product designer for Neo4j, Andreas Kollegger.
Thank you all so much. Thanks for the warm welcome. Thank you to Work Market for letting us have this meet up here tonight. Work Market, of course, turns out to be a perfect application for graphs. I'm very happy that now this entire deck might just be oriented towards talking to them and trying to convince them that they should be using Neo4j. But really, I want to talk about the broader applicability of graphs, and graphs that are all around us, and that any amount of data that you have, any data that you have, has graphs in it, and how to start thinking about that, and then how to start programming with that. And for me, my graph story actually started in this place. This is Chilenje Clinic in Lusaka, Zambia. Some number of years ago, after I was working at NASA, I went and did some social good work around the world, and I got involved with a fantastic program that was developing the nationwide medical record system for Zambia. And I loved it. It was fantastic work. I had never before realized that as a technology person, I could do really cool technology stuff and work with rockets, and that's really awesome. The space shuttle is a fun thing to go visit. But also I could do technology stuff that would have social good impact and that would make a difference in the world. And I hadn't really realized that until I got involved with this project. And particularly about the technical challenges that are present in a resource-constrained environment where you may or may not have power, where there aren't networks everywhere, so there's not necessarily even anything better than a cell network that comes by every now and again to get you access to things. Presented fantastic technical challenges, but also very gratifying challenges to tackle, because everyone that you tackled, more people could actually get advantage of the medical records. So let me talk particularly about what we were doing, though. So it was a medical record system, pretty similar to actually medical record systems here in the United States. Serves a couple of different functions if you're doing medical records. First thing you do, if you're a doctor, if you're in a caregiving situation, people come in and you ask them subjective questions about what's wrong. They say they're feeling faint, they've been fatigued, they haven't been able to sleep, maybe their arm hurts, whatever happens to be wrong with them. People have subjective opinions about what they think is wrong. You write those things down. The next step is always to take sort of objective measurements of those people. The basic things. What is their blood pressure like? How tall are they? What do they weigh? Any kind of information that might help you get a sense of where do they fit demographically in terms of a healthy person, whether they're older or younger. You can get a sense of what might be going wrong depending on what they're complaining about. Based on that, you generally then just try to write up what you think your conclusion is about what's happening. And then based on what's happening, you come up with a plan to try to make things better. This is the basic form of doing healthcare for patient care. Seems pretty straightforward, right? Pretty simple. It's just a form to fill out. So this is fine for patient care. This is fine for actually helping decision support. Once a doctor has filled this out, can hand it off to nurses. Nurses know what to do. They've got a plan to follow, and patient care can proceed. We need to add a little extra data to this if in a situation like we were in Zambia, and also in any of the hospitals here in New York City or anywhere in the world. It's not just about patient care. There's also administration overhead and people who are paying the bills. Or in our case, we had public health researchers and the WHO who want to know whether the work that we were doing by providing medical record systems were having positive outcomes or negative outcomes. So in addition to the patient care bits of the form, you end up adding these coding bits of the form that capture what does the patient actually have according to some diagnostic ontology. Take that number and you write it down. What procedure is being performed, there's a code for that. All the little things that could possibly be done to people, there's a giant catalog you can choose from to find the number that fits best, and you write it down in the form. This has a number of challenges, including that the available codes are just huge. To be familiar with all the possibilities is very difficult. And it's a subjective call, actually, at this point, to really map it to exactly what you think this person may or may not have. But it works pretty well. Doctors who are well-trained can use this kind of a system and actually go ahead and do the reporting, and we can figure out what's going on with the populace based on this. So this is a form-based approach to doing patient care. You fill out a form, you add a couple extra numbers to it, you take all those numbers, take all the information that's put in, And generally, you'd end up storing that in a relational database. This is perfect. This is like the classic 1970s why relational databases were created. People had paper forms. They were tired of the paper forms. They started to recreate those paper forms in digital. And when they did that, relational databases ended up being the winner for like how you actually store all that stuff. The relational model was what people used. We all know this, right? This is not news to anybody. Okay. This basic idea of just having a form, adding data to it, continues and it continues. As you want to get more information, you have to add more boxes, you have to add more tables, you have to continue to elaborate on your schema. We've probably all done some level of this in whatever we're working on today, right? So you just add more forms, you add more things for people to fill out. Some things get left blank, it doesn't matter. Ultimately, you capture all the bits that you think you need. But for the actual patient care, how does all that extra information that you're trying to be very particular, very precise about actually help them? It's just more information for really a doctor to look at and make a diagnosis, right? So the doctor starts by starting with the patient's complaint, particularly. And then you make connections with, okay, they're complaining about fatigue, they've got a little bit of soreness in one of their arms, okay, they're a little bit older, maybe they're overweight. So you figure out all of these relevant tests, and what does that maybe indicate? Maybe they're, have early warning signs of a heart attack. You should take some action around that. But what other factors come into play? You might want to consider what their occupation is. If they're working for a startup, then they could just be stressed out. They could just be having an anxiety attack. Different than having a heart attack. So you also then look at things like family history. Of course, if you look at family history, the same connections end up being available to you. Family history has all the same kinds of records you want to pull up, and you want to try to correlate those records with this person and see if there's a family tradition of like people having heart attacks or people having other conditions that you might want to factor in. And if you want to be super thorough about like all the possibilities and really understanding what could be happening with this particular patient, you also look at other patients in that area who are exhibiting similar symptoms. So people who are in the same age range, who are living in the same places, who are complaining about the same kinds of things. You factor all of that in, and then you get even more data points to try to understand. And of course, within all of the data that you've been adding there, in between the data itself, there are implied connections that maybe aren't there within a medical ontology, but they're there within the mind of a medical expert that understands like how epidemiology works and how a disease might progress, the early warning signs versus later signs of like having a disease. Of course, that's not really all of the data. There's more to factor in if you really want to focus on patient care rather than a billing system. For patient care, you care then something about if the doctor who's recording these things or a caregiver, what are their local language idioms for expressing what's wrong with somebody? That may not map directly to like some perfect code in the ICD-9 catalog. You have to understand epidemiology, you have to understand cultural norms, environmental factors come into play, whether there's agricultural practices that are happening. All of these things together actually end up letting you know what's wrong with this particular patient. Luckily, there is a system available that can do all this work, and it is brilliant. It's us. We can do this work. We can do this work. Our brains are wired for this stuff. All of you here in this room are wired for thinking this way, for making these connections about all this seemingly unrelated information that if you've seen enough of, you train your brain to suddenly see patterns where somebody else may not have seen the patterns. And if you're a doctor, if you've trained your brain for patterns of medical information, you can then make a diagnosis with the information that's been provided, even sometimes when it's very little. Of course, the more information that's provided, the human gets smarter and smarter and can actually narrow down the possibilities. It's suddenly like a chess game of eliminating the possibilities of what might actually be happening with the patient, and you can come up with a proper diagnosis. Okay. That's all fine, but I was building a medical record system. So we want to actually be very computer sciencey about this stuff, and we have this relational database, and we continue to add to the schema, we continue to add special tables, tables that act as buckets, tables that have represented ontologies, tables that have represented translations to different languages. And for just doing a simple form to present to a patient or a caregiver to fill out for a patient, suddenly the joins and everything that were going on behind the scenes were absolutely ludicrous. It was frustrating to even just try to do the coding. This is less than fun. There's a different way, of course, to think about the data. And this will not be a surprise to anybody who showed up today. If you think about the data first, the way it's represented within a relational database, this is fairly typical with any relational schema in the world. Everybody at some point has to do a join table. And this is a simplified problem for what we had within our data set. Our data set had tons of joint tables for all kinds of special reasons. In this particular simplification, we've got some person who's named Dan going through a joint table to a bunch of possible symptoms that they're exhibiting. And through the joint table, we can say that they've exhibited multiple things. We can say when they've exhibited, perhaps we can add some extra information to the joint table. It's kind of normal stuff, right? When you look at the joint table, though, visually, you can already see that most of the data that's there, you don't care about. Dan doesn't care about all the rest of the data that's in those stacks. What's relevant to Dan and Dan's care is him and the things that he's directly connected to. And then, as we saw in the form, all the other people that might be connected to those things. It's the relationships that matter for understanding what's wrong with Dan, not which stack of tables that he's a member of. This is graph thinking. It always starts off simple. It starts off with a couple of round circles and then little arrows connecting those circles. These are nodes, these are relationships. This is a simple idea of a graph. This simple idea of a graph can represent all kinds of different things. It can be a little logistics network showing traffic that's running on different roads that has traffic lights and maybe different speed limits. That same little triangle can represent things for if you're running a hotel around here, you've got room availability in a calendar. It's just connections. It's the same kinds of data you already represent in a relational database, but now you're thinking about how these things are related rather than looking at the individual records. And once you have these simple patterns, once you've started down this path of looking at all the relationships and understanding that having relationships isn't the end of your day, it's not going to make you miserable having to do tons and tons of joins. Once relationships are good to work with, you're not afraid of them, you start adding more and more of them. So a simple social network has more people that are added to it. You might start factoring in where these people went to school, what jobs they have, maybe things that they've purchased. And from this, you can end up with a social network that is also a professional network. It can morph into being a product network. Anything that you have that actually has people always has a graph explicitly within it, because we form a social graph. We are social network, we're social humans, right? Social beings. So there's always a graph when there are people involved. So as long as you have customers, you've got a graph. Elaborating all of these simple patterns eventually, of course, gets to be a big, giant graph. And one of the fun things I like about these big, giant graphs, and it could have almost been a trivia question, is that almost no matter what the domain is, at scale, all graphs pretty much just look the same. They have the same kind of blobbiness, they have the same kind of clumpiness in different areas, they exhibit various outliers, and the small patterns and the macro patterns are similar throughout. The beautiful aspect of that is once you start to understand graph patterns and how to do graph thinking, that graph thinking that you have, you can apply to any domain. The lessons you've learned apply to all those domains in a way that having become an expert in some relational schema does not necessarily apply to some other relational schema. You can't just directly transfer those queries. You could transfer, with very little modification, queries you have that are graph queries into another domain and have similar results. We'll take a look at some of those. So actually, right, first, what does it mean to do graph queries for writing them? If joins are so terrible, and it's better to write queries with a graph. With Neo4j, we have a graph query language. We call it Cypher, which I don't have something to throw out as a trivia prize, but can anyone guess why Cypher is the name of our query language?
Circle.
What's that?
Everything goes back to
It's not because of a circle.
the matrix.
The matrix is the answer. Because Cypher is a character in the matrix and the Neo in Neo4j.
And you're Keanu.
What's that?
And you're Keanu.
I'm sorry.
And you are Keanu.
And I'm not Keanu, no.
You're the Oracle.
I am the Oracle. That's right, I am the Oracle. The new Oracle. We'll take a simple graph to look at how to do queries with Cypher, our beloved query language. If you had some Dan who loved somebody named Anne, it's a very simple graph. To express that, you've got the circles, you've got the arrow, you've got properties on those people. If you want to find Dan and Anne and the fact that they love each other, you would just have a match query. So match says, I'm going to describe a pattern to you, and I want you, Neo4j, to go find instances of that pattern. And the pattern that you described here is one node, where the first node is a person, and then the person has a name of Dan, and has a loves relationship to another person whose name is Anne. You can kind of just read that left to right, and that's pretty much what it does. match a person named Dan who loves a person named Ann. The Dan and the Ann are our nodes. In the middle, we have a loves relationship. The nodes have labels, they've got properties. This is pretty much just a simple property map. You can add as many properties as you want to. There's no schema to work with, so you can just add things as is appropriate. And then you can write queries with it. To see how easy it is to write these kinds of queries, this is a bit more of a businessy example, where if you wanted to do this, if you want to find all the direct reports in some org chart, how many people are managed below you, and then how many people they manage up to 3 levels down. So just trying to figure out, like, what your current density of middle management is, right? Here's what the SQL query looks like. And this is actual code from one of our early Neo4j converts. Could you just imagine A, having to write that, and then B, maybe having to maintain it when there's something wrong or like something has to be changed later? Come back to that code just a week later, and it's impossible to actually figure it out again. Here's the Cypher equivalent. Fewer lines of code, a little bit more English-like. You can actually kind of read and figure out what it's doing, right? So here we're matching some boss who manages some sub-managers, and those sub-managers who manage their own reports. And where the boss is named John Doe. Pretty simple and straightforward to read. And then based on that, we want to return the names of the subordinates and a total count of people reporting to them. This is simple enough that anybody within your organization can write this kind of stuff. This doesn't have to be specialty, DBAs who are writing this kind of stuff. And if you're a specialty DBA, because this is so simple, if you get to the point of doing like queries that we have on the right, you can get even incredibly more powerful stuff going on. It would be impossible to write in SQL. So for business users can just understand what you're doing. They can actually do some of the work themselves. They can actually do their own kinds of queries in the database. And DBAs and developers can actually write much more fascinating queries, much more interesting recommendations and pathfinding than would be possible if you were doing it just with SQL. This is good fun stuff. This is the kind of stuff that I wish I had back at the clinic. So graph thinking in practice. Graphs, I wanted to use graphs when I was doing the work at the clinic. We found that, of course, as soon as we had a commercial offering for Neo4j, the initial uses were the typical uses of people had a social graph. So they've got a social graph, they'll use a graph database for representing it. There's a pretty clear mapping for them. The other set of people that were early adopters of Neo4j had a relational database, and they had a join table that was just crushing all of their performance. And they simply took that join table and moved that into Neo4j, and then managed having some queries in Neo4j and some queries in their relational database. Usually when that happened, we were really gratified that, like, more often than not, it'd be some Oracle rack that somebody was paying not an insignificant amount of money for. And then we would replace the most significant queries of that Oracle rack for like 1/10 of the price. It was fantastic. Other things you can do with Neo4j, with graphs, things like doing real-time recommendations. Recommendations is one of the foundation query patterns you'll find within graphs. Once you learn how to do a recommendation pattern, you can apply that to any domain, whether you have product recommendations, whether you have a work marketplace and you're trying to find people who have things, people that want things, or people who have skills and people who want those skills. Recommendations are really awesome to have like in your back pocket, always to be able to pull out. One of our customers, of course, does that kind of stuff is Walmart. They have a product catalog, they sell stuff. So this is the classic, if you bought this thing, people who bought this thing also bought this other thing. That's what we want to recommend to people. Another use case that to be honest, like when I first encountered this, I had no idea what the letters MDM stood for. That would have been a good trivia question for me as far as acronyms. Master data management, how many people work with it, know it? Oh, okay, you're all much more smart than I am. This was new to me, and I was fascinated by it. I guess it's really the term du jour for business objects and business entities that matter within your company. Usually it scales from your organization itself and touches all of the things that are key in your organization for actually deciding whether or not you're going to be profitable. So it's typically a lot of org charting stuff, so how your organization is structured. And of course, the structure is never a tree. It's always messy because within the tree, people cooperate on different projects. There are things that have to go through a workflow that start in one part of the organization and in some other part. You want to map all of those things and map all of the user touch points all into one graph to really understand what's happening in your business. For master data management, that was one of our early adopters from Cisco, who internally had a huge master data management challenge. They've got a product called HMP that is a used for governance and single source of truth and one-stop shop for all of their hierarchies. Yeah, it was basically, they had a huge organization, so many people spread throughout the country, spread around the world. And just to understand who was where and who might be affected by something was a hard problem for them. Putting that all to graph, let them actually work with that pretty reasonably, and they've been big fans ever since. Something fairly late coming actually to graph awareness for us was fraud detection, and yet it's a beautiful application of graphs. Fraud detection is actually like a special case of doing recommendations, where you're kind of trying to do like almost an inverse recommendation. You're trying to find the thing that doesn't fit. So you can find patterns of behaviors that don't make sense rather than trying to recommend a pattern of behavior that you want somebody to do. Fraud in the simple cases is easy to detect. When somebody manages to steal my credit card and ends up in Peoria and buys a Ferrari, that is going to get a flag. Some bank is going to be smart enough to realize that I have no reason to be in Illinois. I don't have enough money to buy a Ferrari, and so all of that looks like it's clearly not the right behavior for me. That'll be marked. That's an easy one. Much more difficult is the fraud where a number of people collaborate together to fabricate identities. So rather than just stealing one person's credit card, you actually create an identity based on an actual person with a social security number, and you grab a phone number that's real, and you grab an address that's real, you grab bits and pieces of a person, or reconstituting a person. And with that, you actually then engage in fraudulent behavior. And that's much more difficult to detect. This is the classic case where the best lies are close to the truth. It's the same with fraud. The best fraud is close to legitimate activity. It's just a little wrong. Very hard to detect on its own. What's that?
I said like the stock market.
Like the stock market, like this has some relevance and apologies to anybody in the room if you were personally affected by it, but this has relevance to banks in the stock market here in New York. There's a lot of fraudulent activity that would be easier to detect when you look at it as a graph. Graph-based search is something that we're happy that Facebook has been a champion of with their own graph search within Facebook. This is just taking advantage of the graph for actually letting people directly kind of navigate it to find things that are relevant to them. So rather than it just being the backing of an application, the graph is an application for people. People can actually see who they're connected to and what they might want to find by just asking questions that are very natural seeming questions for them. This is actually related to something that Lufthansa is doing with all of their digital assets that they're managing for their in-flight systems. The way that they craft all that, the way they present that to users is a very sort of graph search approach. This one I love. There's a use case here that I might want to take a minute. Actually, how much time do I have right now? I'll do a time check. Doing great on time, right? Plenty of time. Okay. So I'm going to take a little minute with this one. Network and IT operations is a lot of fun because, of course, a network is a graph. And so it's a very natural thing to want to model as a graph. So that you can do things like figuring out like which component in your network is the most dependent on things so that if it fails, your network will go down. That's going to be the thing you want to have redundancy around, so you can do capacity planning around that kind of thing. And it's really a lot of fun. There was a telco in France that prior to discovering Neo4j and discovering graphs, they essentially had that problem. They had the problem where for them to manage this telco network that spread around the country, they didn't have a good sense of what customers were dependent on what pieces of equipment. And so whenever they need to do some normal maintenance, which equipment fails all the time, you've got to send people out in the field, trucks show up, and something gets powered down, gets replaced, and gets powered back up. Before they could do that, they would spend a week doing the analysis, and then they would send a crew out. That's fine when it's scheduled maintenance. It's a little less fine when lightning strikes, and you're not sure what just happened, where it happened, or who got affected, and you've got to reroute a bunch of things. Turning around modeling that in Neo4j, you can do both things in real time. You can suddenly have your entire logical network, physical network, logically also modeled. So when something goes wrong or when something has to go down, you know exactly what to reroute, what kind of planning to put in place, and just make it happen basically at the same time you're sending the crew out the door. It was a lot of fun. HP is actually doing something like that with one of their systems. They're actually using this sort of embedded in one of their products that they offer for doing network topology analysis. And it's basically the same kind of thing. They figure out what the network looks like, and they automatically figure out when alarm bells go off, where the problems are, and like have people actually go off and like do the right things for response. Identity and access management may or may not be as obvious as a graph problem. In trivial cases, just user management and you have permission for this thing or not is pretty straightforward. It gets much more complicated when what you're managing is access for physical things or for services that you're offering to other people, perhaps to other businesses in a B2B type environment. And that's something that actually UBS actually turned to Neo4j for, where you need to have identity access management for a system of services that is constantly changing and is managed by you, but on behalf of another company that itself is always changing. So to provide all the necessary parts of control for it to be actually flexible enough for capturing all the different groups and subgroups and plans and specialties that might be going on, for deciding whether one particular person, for instance, is able to unlock this particular net vault, it gets complicated. Putting that all in a graph makes it really easy to understand what's going on and whether that person should be able to turn the key. And of course, graph thinking has created some of the most successful businesses on the planet. This one's easy. LinkedIn basically mimicked what we do with newspapers, or used to do with newspapers, where if you're looking for a job, you just kind of somebody posts that job in the back of the newspaper. If you're looking for a job, you go to the newspaper, you follow through it, you look for jobs that look interesting, you call people, you maybe send in a letter or something, and you try to get a job that way. The brilliance of LinkedIn, the real success of LinkedIn, is turning into what had been a job search of just random calls into a professional network where they're mimicking what we actually do as people when you want to get a really good job. We know that from life experience for all of humanity's history, that to get a job somewhere, the best way to get a job somewhere is to know somebody who already has a job someplace, or to know somebody who knows somebody who has a job someplace. Of course, the further out you go into knowing somebody who knows somebody, the weaker your recommendation ends up getting. But still, the best chances you have is to try to find the shortest path from you to people that you might know who work somewhere, and then to work them to look for positions and then recommend you. Personal recommendations for jobs still dominate all job search and all job success. That's essentially what LinkedIn did, with their professional network. That's the great value out of LinkedIn, is as a big job marketplace. Much more famously, I think, of course, is the graph application that made the difference between all the other searches that existed pre-Google, and then once Google showed up, nothing else mattered. And it was because of PageRank. And PageRank was just a graph algorithm. It just said, what matters about these pages when you're looking for stuff on the internet is not what the page says about itself, or what meta programming it tries to do for keywords that it puts on a page, or how long the page is, or how exactly it matches what the user is looking for. None of that matters. What matters is how many other pages think that page matters for that thing. Of course, then there became a bit of a game system and an escalating war of trying to game the system of how PageRank works. But the fundamentals of PageRank, the fundamentals of the knowledge graph that Google has moved to since then is all graph thinking. All of the pages that you find when you search with Google are based on looking at how that page is related to other pages and how you are related to the other people and those pages that think that it matters. It's because of all those graph connections that you get graph searches and then Google results. Back to slight relevance here for New York, a little bit more close to home. Banks were very hesitant to come online and do any kind of online transactions, have online web portals, and anything like that, because banks were concerned about fraud. Fraud is a huge problem for them. Mitigating the losses from fraud is a big challenge for them. And so the idea of going online where you don't see customers face to face, you don't know who people are, you only kind of know that they've got an email, and then trusting them to actually do credit card transactions is really a scary thing. PayPal's big insight was that they could mitigate potential for fraud by having a trust network that was based on who you were, what transactions you've had that have been successful, and then understanding whether or not you yourself are at risk, and then whether or not letting that risk assessment actually get passed on to any of the vendors that might adopt PayPal, so that they could mitigate their losses as well. And by having a network approach and understanding what the potential risk was for an individual transaction, that let them lower the potential for fraud, and and then actually had an online service that was pretty safe for actually committing any kind of economic transactions online. Since then, of course, we've gotten Bitcoin, we've gotten additional things that have come online. Fundamentally, it's all been about a trust network that actually lets us do online commerce.
Yeah, but that's blockchain, not Bitcoin.
What's that?
Blockchain is what drives the new consensus network.
That's true, yes.
Bitcoin is just the currency.
Yeah, fair enough. The technology behind it, right? Okay. This has been a recent story that I'm personally very excited about. And as I started off, the talk earlier, I came into Graphs because I was engaged in doing social good. And when I switched from that focus of my life to actually joining Neo4j and working for Graphs, the conversation that I sat down and had with one of the founders was around the potential for this technology to also have social impact. I realized that if I had Neo4j, the stuff I wanted to do in Zambia would have been way easier. Without it, it was a bit irritating. And we both thought at the time that we could have social impact, that if we were successful, that the true measure of our success would be that graph thinking would be kind of normal, that people would use graph thinking the way that they use relational thinking, they would use it in the right times, in the right places, for the right kinds of problems, the right kinds of questions that they wanted to ask. And that if it's pervasive enough, some good can come out of it. And then this happened. I can't tell you how gratifying this was to hear this story, and we didn't even know any of this was going on, of course, because it was super secretive. Like the journalists involved had to be incredibly careful with the data, how they're handling the data, what they were using. And it turned out that they were using graph thinking, and that they were using Neo4j for actually doing some of their analysis. And that's how they've actually been distributing their data now. I love the story. Does anybody not know about Panama Papers? Okay, good. Okay, just in case you don't know, the quick background on it is this. Oops, back up slide, sorry. See if I can avoid this skip. Good. So the Panama Papers is really just, it's a giant leak of files from a company in Panama, a law firm called Mossack Fonseca. And the anonymous source, still anonymous, who leaked the data, leaked it to a German newspaper called Süddeutsche Zeitung, South German newspaper, I guess? Any German speakers? Yeah, okay. They loved this leak. They thought it was awesome, but they're a newspaper. They don't really have data scientists, so they didn't know what to do. They turned to a company, or actually an organization called the International Consortium of Investigative Journalists, the ICIJ. They enlisted the ICIJ to collaborate with other data journalists around the world, because this was a huge global data set, and go through all this data and try to reconstruct what it represents. So the ICIJ actually did all the organization, they did the bulk of the analysis, and they were using Neo4j. The group that collaborated on this was amazing. It was airtight secrecy among like 300 or so different collaborators from 100 different media outlets in 76 countries around the world. I mean, kind of on the flip side, like that's an amazing conspiracy to kind of pull off, to like keep that tight-lipped and like under control, to actually do all the analysis, and then finally release things was pretty amazing to me. The data itself is also, of course, pretty fantastic. If you look at the upper left there, the 1.7 gigabyte, that's the size of WikiLeaks. It's, very important, very significant leak of data. The big red series of blocks was the 2.6 terabytes of physical files that were released as part of the Panama Papers. These things are, 11 million different files that constitute emails, there's financial spreadsheets, there's passports, corporate records, lots of fascinating things that are like contained within this. All raw files though. It's basically like having a giant zip drive or something with all these individual files. What the journalists did is go through all of that and try to recreate a database so that they could then do analysis with these files. The individual files themselves, of course, interesting, not really that useful for doing anything like asking some questions. So they recomposed it into a graph. The graph that they've created is, for us, a modest-sized graph. It's a tiny little thing, just a couple 100,000 nodes, a million relationships. One of the journalists, Mar, who presented at our conference in London recently, was very sheepish about this. She was like, I know you guys deal with like millions and millions of things, like big data and all that, but this is still really incredibly significant just because of what the actual data is. It's about 4 gigabytes on disk, and it has a combination of explicit relationships where within a particular document you could understand exactly here's what this person is, here's another entity, here's the relationship that they have. You can be very exact about that and explicit. And that's for shareholders, officers, for the corporate records, things like that. You knew those things for sure. But then they also added in implicit relationships for things like when a name looks like it's similar, but you don't know for sure that it's the same name. In this data set, they don't always have available to them something like a social security number to know that the person who is on this form over here is the same as that person over there on that other form. If you took somebody like me and stuck me into this world, I've got 3 names. I've got a first, middle, and last name. So Andreas Kollegger is my name. I could appear a bunch of different ways on these documents and still be legitimately me. I could be A.Kollegger, I could be Andreas Kollegger, I could go with Andrew Kollegger, people would probably accept that. I could go with Andy Kollegger. I could throw in the middle initial, I could take the full middle initial, the full middle name. All of those would be legitimate on legal documents, depending on who I'm dealing with. But by doing that, it can kind of hide who I am if I want to be a little bit careful about who I was, like not let people be very obvious, not be very obvious about what kind of activity I was engaging in. So that's the other part that they did is they ran a lot of analysis on name similarities and put in place those links as well, so that when it seemed like this is probably the same nephew of Putin, they would go ahead and make that connection so you could do the analysis with it. Okay, so the impact has been pretty fun. Most impactful, I guess, for the different nationalities was that the Icelandic prime minister had to resign after these revelations came out. It turned out that he had a bunch of offshore banks in which he was putting funds that were then turning around and buying Icelandic bonds at a time when the Icelandic economy was failing. So he was basically betting against the economy actually at some point.
And his sister.
Was that and his sister?
He was suing for his sister.
That's right. So it's which is classic both in actually this is classic fraud ring stuff. Like you usually engage a very small network of people that you have a lot of trust with. All of them do a little bit of it, and then in sum total, the fraudulent activity is obvious, but the individual things completely legitimate. And to be fair, within this data set, as it says in the bottom, there are lots and lots of people who have legitimate reasons for using an offshore account, and so they that doesn't mean itself that there's any kind of wrongdoing that's going on. It's important to know, of course. But sometimes there is wrongdoing. There's money laundering that goes on, and when you can follow the money back and find all the people who have been doing all the money laundering, things like cartels can actually get linked in, and arrests can actually happen. Pakistan's prime minister had to leave his country. The Spanish prime minister also had to resign, and I think most hurtful for some members of the journalist community, because a lot of them were Spanish, that FIFA was hit pretty hard from this as well, because there was a couple connections to some famous soccer players, particularly some players like Messi.
That was not a
surprise. No judgment on people, but yes.
It was a question of when.
That's right. It's just really when and then who exactly it would be. So FIFA is maybe not the most upstanding of organizations. Okay. If you're curious about this, oh, sorry, you have a question?
What are the negative implications of that? I mean, for sure, these kind of things were going on through entire human history. It's just that we got the technology right now that we can, piece by piece reassemble that in the way that nobody was expecting. So you can suspect that anyone who is in power, or has money, or has connection, or has anything at some point, going through ancestry, there were some shady things were there. I mean, what is the significance of all of this?
So the difference here is that we have to. I think you're right. To be cynical about humanity is always going to find ways to some people always find ways to cheat or to do things that they're not supposed to be doing and to hide their activities. That's always happened. It'll always happen. Politicians have a mixed record themselves, of course, around the world. There's very few that are completely innocent of any wrongdoing. Compromises happen. Things occur. The significance of this is that it's now obvious. It's now transparent. It's one thing to acknowledge and just sort of say, okay, we know that all politics is corrupt, and have conspiracy theories about it, and that's fine. But if you want to do something about it, and if it's actually affecting things, the only way to have any sort of laws come into place to help regulate politics or regulate money in politics is by more transparency. That's the theory of the journalist, at least.
Yeah, I mean, but this also has a parallel with, the financial regulations and KYC and being able to say, do you know where this person actually is and track their money across wherever? Because basically, Uncle Sam is going to look for their money no matter where you are in the world. So that plays a big part in it.
In the case of Iceland,
people
Iceland
want
was
the time.
bankrupt. The country was bankrupt. So bad enough the man was stealing. He was stealing.
Well, I was in Iceland at the time when it was bankrupt. It was, pretty nice place to be, pretty nice restaurants to eat,
No
pretty
argument.
nice, things for the people. Much better than here in New York.
No argument, but the country was bankrupt.
Yeah.
So what?
I think the point is simply that it gives us something to talk about. Yeah. So I mean, this is it's another way of actually just thinking about things. It's another way of actually understanding what's happening in the world around you. If you want to take a look at this data, if you have any curiosity about it, you can download the data set. You can get the raw data files. You can also get a packaged up Neo4j that they put together that also has the data to look at. Okay. Enough about use cases and fun politics, and we can take some more of that afterwards if you'd like to. It's always fun to talk about. Let's talk about future technology and something called Core Edge. Okay, for Neo4j, for a graph database, the key to scalability is figuring out what to do with relationships. Relationships are everything for what matters about why we're fast and the kinds of queries that we do, how we represent relationships down to disk, and how we manage caching up and down, how we actually have a cluster, and how we have transactions that occur across the cluster is also, of course, got to do with relationships. Relationships really matter. And they affect, when you do queries with relationships, it's that it can touch a lot of data. You don't necessarily even know where the data is going to be. And this is where the real challenge is in having graphs that are larger than a single machine. If you want to partition a graph across lots of different machines, it's easy to do that. It's hard to do that well. It's hard to do that and not also have a huge penalty in performance. So if all you want to do is store lots of data, great, awesome. But if you want to query that data, it's not really going to be a big advantage unless you can partition things in a very good way that your queries still run without a lot of hops across the network. So for real-time queries, you want to have consistent response times, particularly, of course, if it's a user-facing application. You can't really suffer a query that sometimes goes in milliseconds and sometimes takes 3 or 4 seconds. That's just no good. It has to be pretty even. And of course, you want to get the same results every time you ask a query. You want it to have some level of consistency, some way to expect correctness in the data. Okay, so for us, these end up meaning that there's a next step of requirements that we have put for ourselves as Neo4j as we're developing the next generation of what we're going to offer. And the biggest thing really is that we already have a clustering solution that we're very happy with. It's used by companies around the world, and it's awesome. But we want it to be even better. It has to be nonstop. Once it goes live, we want it to always stay live, continuously operating, scaling up as you need scale, the way that you expect, everything that magically happen in the cloud these days. Those are the new things we want to do for Neo4j. While we're doing that, we want to guarantee that we do that in a way that maintains high levels of throughput, and that everything is optimized for doing graph-like queries, because that's the whole point of using Neo4j, right? And those graph queries have to be super low latency. If you don't care about latency, if you can, wait a couple minutes for something, if you can just do it in batch jobs overnight, then having a live database for this stuff doesn't really matter. You can probably store that in anything at all and get along with it just fine. So for us, we want to be live, we want to be real time, we want all of the decisions that are being made based on the data to be the latest possible accurate data. And of course, there's this bit. As the earlier trivia mentioned, we're from Sweden. Swedes like to crash things. Volvos like to be safe. They crash things over and over and over again to make sure that safety is number one. That's true for Neo4j as well. We care about safety a lot. We care about it so much that in our release process, we spend, it's just short of a week now that we have this absolutely amazing farm of Amazon machines that goes out and runs a battery of tests on things. And included in the battery of tests is a lot of tests that try to be just mean to the database. Power a database up, let it start running, kill it. See what happened. Power a database up, kill it. Keep doing that over and over again and see what the impact is to the data. Neo4j today handles that very well. It's very resilient. You always get either transactions are committed or they're not committed, and you get the actual data that you expect. As you scale out and you want to have even larger graphs, continuing to maintain that becomes quite a challenge. And we have some strategies for trying to address that in a way that I think is going to be good. The first part that we're trying to address is that our current clustering architecture is based on Paxos, which, if anybody's familiar with Paxos as an algorithm, it's academically, magical and awesome and good. In terms of implementing Paxos really, really well, it's really, really, really hard to do. I have to admit that this is not part of the code that I had anything to do with. I bow down to the people who had to write any of the Paxos implementation stuff. But we're going to move past Paxos. We're actually moving to a new algorithm for consensus called Raft. It has some of the same properties as Paxos, but it's much more resilient, it's much more robust, and we think it's actually going to let us scale a little bit more. In addition to using Raft, we're going with a new deployed model where we have essentially two clusters collaborating together that we're calling a core cluster and an edge cluster. The edge cluster you can think about as being what you do with websites when you want to scale out and you sign up for a CDN. And the CDN is just there for caching geographically distributed results for people. So some stuff is pulled off of the edge, and things that really matter, you can go right to the core. So if you're doing interactions with a live website like Facebook, static images and things might get served by a CDN, but when you're updating your status, that doesn't go to the CDN, that's going to go back to the core, right? So that's the basic model here. Core servers for the resilience, the edge servers for scaling of the reads. One important thing for us about the edge servers is that the way this is set up right now, you can just add edge servers as you need them. So as you find you have, you need more capacity, you can just add to the edge set. And the edge set, actually I guess I've got a diagram about that. The architecture is pretty great for how you can scale up and how things get populated as you bring in new things, new servers to the cache. The other aspect of this is that it gives us an opportunity to present to users different options on consistency. So depending on the operations that you're performing, you can decide what level of consistency you want to have for that particular query. And I'll get into that a little bit. Oh yeah, okay. Of course there's forgot about this. So for us, being Swedish, being a database that's always cared about, atomic transactions, ACID transactions, writing to disk is always important. When you do writes have to go to disk. They have to actually be committed in a way that doesn't break the data model. It's incredibly injurious to a graph, the way that it's not to a document database or a key value store or something, to have a bit of data be partially written. You can have a single document that's broken, and it only affects that document. It's not really a big deal. The pattern we've seen over and over again with databases that don't have consistency guarantees around writing graphs is that once you have a broken relationship, let's say, that goes from one node, and then there's a relationship but the other side isn't there, so it's a bridge to nowhere, that failure within the data tends to propagate slowly outwards, so that more and more decisions are made based on something that's not true, and basically more and more of the data set ends up being corrupted. So once corruption happens, it actually spreads within the graph. That's why for us, that's always been the #1 job, is make sure that we always commit that down on disk. At query time though, depending if you're doing a write operation or a read operation, your sense of the world may differ. We haven't quite decided what levels of isolation and consistency will allow users to specify, but effectively you'll be able to decide things like, do I only care about reading my own writes? Do I only care about just reading something? So just tell me whatever you know and just give it to me as quickly as possible. Or is the stuff that I'm doing right now so important that it has to be committed all the way back down to the core group so that I know that that is truth? Amongst that set of things, you'll be able to actually do that on a query-by-query basis. A little snapshot of one of the potential deployment architectures. This is a multi-data center thing where you have in data center 1, the entire core cluster is housed right there so that it's got maximum communication amongst all the members of the core. This would be the highest write throughput scenario because the majority within the core has had an agreement for something to actually be committed. So all reads and writes can be committed to that core, but the other data centers plus that data center have a collection of edges that you can just continue to add and send reads to those. there's one little arrow there that's significant. That's meant to indicate that as you add new servers to some new data center somewhere, it doesn't have to ask all the way back to the core group for updates. It can ask its peers. It's a little bit like a BitTorrent kind of scenario where like anybody can be a seed for actually feeding you the data that you need. So as long as somebody has transactions that you need, you can pull from your local network, or if you have to, you can reach all the way back to the main network.
So there's an assumptive truth there? When you do edge to edge, well, you call it peer, but it's basically edge to edge.
Yeah.
So there's an assumptive that the edge is always correct.
So they might be behind, but they're always correct. So as long as you continue to apply, as long as you follow through the transaction log, you'll eventually catch up and be in the right state.
They're consistent at the timestamp. Right.
That's right. It's so when at any point in time you'll be right. You'll have a snapshot that is correct, and then it'll catch up.
Is your model here to go? What's the speed that you're trying to reach? Is it going to get approach in real time, or?
Well, so our goal, of course, is to be as fast as humanly possible. So realistically, everything is intended, even if you're on the edges. Well, so for writes, it depends on network hops, and then it's really most of the write performance is got to do with like disk speed. So you're limited by that. All writes ultimately end up being serialized down to a single disk, and that at the moment still controls things. For the read, it really is just network. Once you have the replication everywhere, the other thing that comes into play is that you end up getting some amount of caching in memory for that particular server. So depending on where requests are going, you get memory speed access for parts of the graph. If you think, partition things well that way. On the right side, the next step here, after we've deployed the new Raft algorithm and we feel pretty comfortable with this, we already have work going on for the next step, which will be having what we're calling multi-Raft, where we'll be able to do multiple writers for a partition graph. And that's the only way to actually increase our write throughput.
And Raft, I'm sorry, is that proprietary, or that's also open source?
No, Raft is an open source algorithm. There's actually a Raft spec on GitHub that you can look at, and there's a bunch of great animations that they have out that actually describe how Raft works and how the communication happens.
Yeah, but I guess with just edge servers, if you lose your core partition, what happens to the consistency of your edge? Or essentially,
So
if you have this multi-distributed environment.
Yeah, so if DC1 goes down,
Yeah.
so you'll still be able to perform reads from everybody else, and they'll catch up with each other, but there won't be any additional writing that you could do.
But how does DC2 and DC3 get consensus that DC1 doesn't exist anymore? Like
So the edges never get elected, so they never actually become part of the core. So the core, you specifically have to have a member within the cluster as being a core candidate. So all of the edges are only ever read-only devices.
Are the schemas consistent across all the edges, or can the schema be, for example, tuned for specific types of performance on one edge versus another?
So they're always exact replicas. So if you've built an index on one of the core machines, that index will propagate out, everybody else will have that index.
You typically don't want to do that because you hotspot. You can hotspot when you try to partition intelligently. You can force a lot of information to go to one host, and that's kind of the propagation problem.
You introduce a lot.
So hang on, I'll take one more question because you've been waiting. Actually, you there with the booster?
Yeah, it's actually my question. So it's one master architecture. If DC falls down, everything you just on read mode.
That's right. Yeah.
And okay, I'm interested, but I'll have to do my reading first. So in DC to this, the right one acts as a local master, but it's again.
That's right. So you also have the option, actually, so I'll show the other diagram here. You don't have to have the core cluster all in one data center. It can also tolerate being spread across a data center. If you do that, the lead, so there's always lead follower. So the lead can actually migrate. It's possible as long as there's a majority agreement somewhere. So it could end up in DC2, it could end up in DC3. That lets you have better resiliency because you suffer having one of the data centers go down, but there's the potential for not having higher, well, not potential. It'll be slightly less performance at that point because you've got to get consensus across data centers. So that's not an ideal scenario. The good part about this is that the consensus only has to be within the fastest majority that can be reached amongst the data centers. So if there's somebody who's, another data center that's, I don't know, multiple seconds of network away, they're not going to slow down everybody else just because they want to catch up. Effectively, the way the Raft protocol voting happens, they'll always end up in a follower mode, so they're always going to be caught up to things. The only advantage of having a really remote, slow follower is that you can still send writes to it, and it will propagate the writes to the rest of the cluster. Okay, one last question.
Do the edge servers need to be a full-fledged database? Can it be something like a proxy? Once we had a squid or a varnish, so why do we need a full Neo there if it's going to be read-only?
So that you can run queries. Yeah. I mean, so these are not like just caches. They of course are like it's similar to an edge cache, but you can run a complete query. You could in fact take one of these data centers or take one of these machines and decide you're just going to have it around for doing reporting, let's say, and you don't want it to be part of like what's the user-facing part of the application, but you want it to have the same data set. So you create a new edge server for that, and you would run all your reporting queries on that. It's an actual database.
Okay, it's an argument.
No, okay, we can talk some more on that too. Yep.
Excuse me, is this
Okay.
based on IDMS, which came out about 35 years ago? It's a network database, and it seems like it plumped up.
So historically, I mean, there's been, and actually I'm not familiar with that one.
IDMS, I think Colonet had it, and it got bought by somebody else.
It's owned by Computer Associates.
Yeah, but it's
Okay.
it's a network. It's a network.
I mean, network databases are not a new idea. Like, it was, early 70s when that stuff had come out, right? And like, it's been around for a while. We've had network databases. They basically lost to relational databases. They were only
Which was a
used-
shame because they were better
I
designed.
mean, it's a lovely model. This is really sort of, it's in that heritage, certainly. Like, it was from the original network databases, and then RDF, rose for a while. We had a brief dalliance with object databases, which we all loved. Which nobody loved.
Speak for yourself.
And so Neo4j is really the latest iteration of that same thinking where like the network is really what matters, thinking that way really matters. Our novelty over RDF or like other network databases is that any of the records that you store, like so the nodes themselves are fat nodes, so to say. Like they're fat. You can store lots of data within a node. It's not like just a lightweight single value. It's a property map, so you can store as much of the properties in there as you'd like to, as makes sense for what your data model is. Oh yeah, so one last thing to mention in things that are coming up next. We've already released this in Neo4j 3.0, and with core edge processing, with that new architectural pattern. Oh yeah, sorry, hey, your phone, you've got your phone.
Oh, your phone?
No, somebody else's phone. Wait, maybe it was a giveaway. It was a secret giveaway. We'll find an owner.
The other guy got up too.
We've also released in Neo4j 3.0 a new binary protocol for communicating with Neo4j. Previously, it was only HTTP. HTTP is fun because it's easy to connect with something with HTTP. Everybody's got support for HTTP. It is not the most performant protocol to actually manage a database with. You've got a couple of problems with HTTP, including that we were using JSON, so like what you could represent in data wasn't really great. It wasn't particularly efficient for having large streams of data either. And you could get in scenarios where if you had a very overloaded server, you could start a transaction and start sending some queries to it, but because it was one connection at a time, you may not be able to commit your transaction because suddenly the server is overloaded with other requests. It's essentially getting a denial of service attack from a bunch of other places. Which once that happens, now whatever transaction you were trying to do that had a bunch of locks on the database is just kind of orphaned while you're sitting there waiting for just an HTTP response. All kinds of horrible scenarios. Bolt is much better because it's a connection-oriented thing. It's binary, so the data transport is much safer and it's much faster. And with Core Edge, it's going to be participating in the network. So rather than just being a dumb connection that just connects to one thing, sends queries, and gets responses back, you can both do tunable consistency. So you can say, for this query, here's what I require, and you might be told, okay, go connect to that other database. Databases can actually go out of service, and they can tell you, hey, this is going down, take all of your queries, go continue them over there. We can move things around. They're not going to participate in the voting, but they're going to be aware of the actual cluster topology. They have discovery endpoints that they can use for that, and they can separately have read connections and write connections and saturate both for maximizing utilization of the network. I think I said all the things in the bullet points. Oh, good. That's all I have. Thank you so much. I've got, I think, a couple of minutes for questions, and I'll be around for questions after that. I'm not alone here today. I've got my associates with me here as well. I've got Bill and Dave. Wait. I've got two associates who are with me as well. If you have any questions about Neo4j, you can come up and talk to me, or grab them as well. We're happy to talk. Do we have time for questions?
Yeah, we do. We're going to take a couple questions. Who wants to ask the first question? Right there.
Are there any other graph databases? Can you do some comparison? Are there any other graph systems?
Not that I'm aware of. So yeah, of course, there are a bunch of other graph databases out in the marketplace. They are a mix of, so there's the classic databases, I'm going to call them a little bit. The RDF world continues to be around. It can be a slightly different model of a graph database, but it's still a graph way of thinking about things. RDF is alive and well. And there are data layers, graph layers that people put on other databases, so you can do graph-like operations. They run into the problem that I described earlier about what you do with consistency if you actually don't have a write that completes fully. But they have other lovely properties that I don't really want to get into too much today.
When is this new shiny world of distributed Neo4j supposed to appear? That's one question. And the second one, why did you go to the route to reinvent the wheel and create another product that goes with Paxos and Raft and everything, and not just to become, let's say, another ecosystem component for Hadoop? It's solving this problem already within its own core services.
Well, because Hadoop is slow. Frankly, so the biggest challenge we have, we're a transactional database, we're a real-time database. Hadoop is great for doing big jobs. Hadoop, even with Spark, isn't really so great for doing real-time stuff. And as far as Paxos versus that, we didn't invent these algorithms. These were actually academic papers that we've adopted. And we just moved from Paxos to Raft because Paxos was incredibly difficult to reason about, and our implementation, while it was needed to improve, that was the fundamental problem we had with actually getting any kind of scale with the rest of the Paxos. Raft is much easier for us to work with, so it's going to allow us to scale what we want.
What is the ETA for that?
We're looking for early preview in fall.
Okay, that's all the time we have for questions now. Andreas will be here for one-on-one questions. Feel free to come up right now and ask him. There's also more pizza. Feel free to help yourself. Thank you all for coming. Thank you, Andreas.
Thank you, everybody. As we mentioned, there's more pizza over there. As you notice, Work Market has problems with scaling. We're not used to having